Imagine this. You're looking at the night sky, a canvas of stars and galaxies stretching back to the beginning of time. Now, zoom out even further, to the very edges of the observable universe. What you see is remarkably uniform, with the same cosmic microwave background radiation scattered evenly across the entire sky. But here's the puzzle. How did such vast, distant regions of the universe end up looking so similar when they shouldn't have had time to interact or exchange information? This is the horizon problem, and it's a cosmic head-scratcher that led to a mind-bending theory called cosmic inflation. Stick around, because we're about to take you on a journey to the dawn of the universe, exploring how a tiny fraction of a second shaped everything we see today. The horizon problem, an overview. The universe, as we observe it today, presents a puzzling uniformity. The cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, exhibits remarkable uniformity across the entire sky. This uniformity is striking because the regions of the sky we see were not in causal contact with each other in the early universe. This is the essence of the horizon problem. To understand it, picture the universe as a vast expanse. Light takes time to travel, and in the early universe, the distance light could travel, the particle horizon, was much smaller than the size of the observable universe today. This means that different regions of the CMB should have no way of knowing about each other's temperature, yet they appear to be in thermal equilibrium. This lack of communication between regions poses a challenge to our understanding of the early universe. It's like seeing two distant cities with identical weather patterns, but with no mechanism for the weather in one to influence the other. The uniformity suggests that these regions must have been in thermal contact at some point, but the standard Big Bang model doesn't allow for this. This is where cosmic inflation comes into play. Inflation proposes that the early universe underwent a period of exponential expansion. During this time, a tiny, causally connected region of the universe expanded to become much larger than the particle horizon. This rapid expansion would have stretched any initial inhomogeneities, making the universe appear uniform on large scales. Visualize a balloon being inflated. As the balloon expands, any small features on its surface become stretched out, making the surface appear smooth and uniform. Similarly, during cosmic inflation, the universe expanded so rapidly that any initial irregularities were smoothed out. This process would have also amplified quantum fluctuations, providing the seeds for the large-scale structure we see today. The horizon problem is thus resolved by inflation, as it allows regions of the universe that are now far apart to have once been in causal contact. This explanation ties together the observed uniformity of the CMB with the dynamics of the early universe, offering a coherent picture of cosmic evolution. Observational evidence of the horizon problem. The universe, as we observe it today, presents a puzzle that has baffled cosmologists for decades. The cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, is remarkably uniform across the entire sky. This uniformity is perplexing because the regions of the sky we see were not in causal contact with each other in the early universe. This is the essence of the horizon problem. The universe is so vast that light, traveling at its finite speed, would not have had enough time to traverse the distances between these regions to even them out. It's like seeing two distant cities with identical weather patterns, but with no mechanism for the weather to travel between them. To visualize this, imagine the universe as a loaf of bread baking in an oven. The heat spreads evenly throughout the loaf, making it uniform. However, in the early universe, the heat, or more accurately, the temperature fluctuations, couldn't spread fast enough to even out the entire loaf, the observable universe. This is because the universe was expanding rapidly, and the speed of light, while fast, is finite. The regions we see in the CMB were simply too far apart for any causal interaction to occur. This lack of interaction should have resulted in temperature differences, but the CMB is uniform to 1 part in 100, 0. This is the horizon problem in a nutshell. The solution to this puzzle lies in the theory of cosmic inflation. Proposed by Alan Guth in the early 1980s, inflation suggests that the universe underwent a period of exponential expansion in its first tiny fraction of a second. During this time, the universe expanded faster than the speed of light, causing regions that were previously in causal contact to become separated. This rapid expansion also smoothed out any irregularities, much like stretching out a crumpled piece of paper would make the crumples less noticeable. When the universe stopped inflating, it was left in a remarkably uniform state, which is what we observe in the CMB today. Inflation provides a mechanism for regions of the universe to have been in thermal equilibrium in the past, even though they are now too far apart to have interacted causally. Observational evidence for the horizon problem comes from the CMB itself. The Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have provided detailed maps of the CMB, showing that the temperature fluctuations are indeed uniform across the sky to a remarkable degree. This uniformity is strong evidence for the horizon problem, as it indicates that these regions must have been in thermal equilibrium at some point in the past. Moreover, the pattern of these fluctuations matches the predictions of inflationary theory, providing further support for this solution to the horizon problem. The CMB is not just a snapshot of the early universe. It's a cosmic fingerprint that tells us about the conditions and processes that shape the universe we live in today. The cosmic microwave background, CMB, and isotropy. The universe, on large scales, appears remarkably uniform. This uniformity is evident in the cosmic microwave background, CMB, the oldest light in the universe, which shows tiny temperature fluctuations of just a few parts in 100,000. This near-perfect uniformity is puzzling. If we consider the finite speed of light and the age of the universe, regions of the CMB that appear close together in the sky might not have had time to interact or exchange information. This is the essence of the horizon problem. It's as if you found two strangers on opposite sides of the world who somehow managed to synchronize their watches perfectly without any means of communication. The uniformity of the CMB suggests that these regions must have been in causal contact at some point, but standard cosmology says they shouldn't have been. To visualize this, imagine the universe as a loaf of raisin bread baking in an oven. As the bread expands, the raisins move apart from each other. In this analogy, the raisins represent galaxies, and the bread represents the expanding universe. Now, consider two raisins on opposite sides of the loaf. They can't communicate or interact directly because the dough between them is expanding too rapidly. Yet, if you look at the loaf, the raisins appear uniformly distributed. This is similar to the horizon problem in cosmology. The uniformity of the CMB suggests that regions of the universe that should be causally disconnected are somehow in equilibrium. Cosmic inflation provides a potential solution to the horizon problem. Inflation is a theory that proposes the universe underwent a period of exponential expansion in its earliest moments. During this rapid expansion, any initial non-uniformities would have been stretched out, making the universe appear uniform on large scales. Moreover, inflation also explains why the CMB appears isotropic or the same in all directions. Just as a rapidly expanding balloon would appear smooth and uniform from any perspective, the rapid expansion during inflation would have smoothed out any irregularities in the early universe. This uniformity would then be imprinted on the CMB, which we observe today. Inflation essentially provides a mechanism for different regions of the universe to have been in thermal equilibrium before they were stretched apart by the rapid expansion, resolving the horizon problem. The standard Big Bang model and its limitations. The standard Big Bang model has long been the cornerstone of cosmology, describing the universe's origin and evolution from a hot, dense state approximately 13.8 billion years ago. It elegantly explains the cosmic microwave background, CMB, radiation, the abundance of light elements like hydrogen and helium, and the overall expansion of the universe. However, this model encounters significant challenges, particularly the horizon problem. This issue arises because the universe appears remarkably uniform on large scales, even in regions that were once causally disconnected. In other words, these regions should not have been able to exchange information or reach thermal equilibrium due to the finite speed of light and the limited time since the Big Bang. This uniformity suggests that these regions must have been in thermal equilibrium at some point, which contradicts the Standard Model's predictions. To visualize the horizon problem, imagine the universe as a vast canvas. Different patches of this canvas should have different temperatures and densities because they were never in contact. Yet, observations show that these patches have nearly identical temperatures, around 2.7 Kelvin. This uniformity implies that these regions must have been in thermal contact at some point, but the standard Big Bang model does not provide a mechanism for this to happen. The horizon problem highlights a fundamental limitation of the Standard Model, as it cannot explain how such large-scale uniformity arose without invoking additional physics. Cosmic inflation offers a compelling solution to the horizon problem. This theory proposes that the universe underwent an exponential expansion in its earliest moments, stretching quantum fluctuations to cosmic scales. During this rapid expansion, regions that were once in causal contact were pushed far apart, but they retained the same temperature and density. When the universe stopped inflating, these regions became the large-scale structures we observe today. Inflation effectively smooths out the universe, explaining the observed uniformity without violating the speed of light. This mechanism also generates the slight density fluctuations that eventually led to the formation of galaxies and other large-scale structures. Moreover, cosmic inflation addresses another limitation of the standard Big Bang model, the flatness problem. Observations indicate that the universe is remarkably flat, with its overall geometry very close to Euclidean. The Standard Model does not explain why this should be the case, as any initial curvature would have become more pronounced over time. Inflation, however, naturally drives the universe towards flatness by stretching any initial curvature to negligible levels. This dual solution, addressing both the horizon and flatness problems, makes cosmic inflation a highly attractive extension to the standard Big Bang model. It provides a more comprehensive framework for understanding the early universe and its evolution. The concept of cosmic inflation. Cosmic inflation is a theory that attempts to explain the rapid expansion of the universe in its earliest moments. Picture the universe as a vast, ever-expanding balloon. In the tiniest fraction of a second after the Big Bang, this balloon inflated exponentially, stretching space itself faster than the speed of light. This period of rapid expansion is what scientists refer to as cosmic inflation. It's a mind-bending concept, but it helps to explain several observed phenomena in the cosmos. One of the key pieces of evidence supporting cosmic inflation is the uniformity of the cosmic microwave background, CMB, radiation. Think of the CMB as the afterglow of the Big Bang, a faint echo that permeates the entire universe. If the universe had expanded at a constant rate from the beginning, different regions of the universe would have had time to cool down at different rates, leading to significant temperature variations in the CMB. However, observations show that the CMB is remarkably uniform, with only tiny fluctuations. This uniformity makes sense if the universe underwent a period of rapid inflation, which would have stretched any initial irregularities to such a degree that they became negligible. Another intriguing aspect of cosmic inflation is its ability to explain the large-scale structure of the universe. In a universe that inflated rapidly, quantum fluctuations in the early universe would have been stretched to cosmic scales. These fluctuations would have seeded the formation of galaxies and galaxy clusters, leading to the large-scale structure we observe today. It's like taking tiny ripples on a pond and stretching them into vast waves that shape the entire landscape. This mechanism provides a natural explanation for the distribution of matter in the universe, which is another piece of the puzzle that fits neatly into the inflationary framework. Moreover, cosmic inflation offers a solution to the horizon problem. Before inflation, different regions of the universe were causally disconnected, meaning they couldn't have influenced each other because signals couldn't travel fast enough to connect them. This poses a challenge in explaining why these regions appear to have the same temperature and properties. Inflation resolves this by stretching these regions to be within our observable universe, allowing them to have been in thermal equilibrium before inflation. It's as if the universe had a cosmic makeover, smoothing out any discrepancies and leaving us with the uniform cosmos we see today. Early proposals of inflationary theory. In the late 1970s and early 1980s, cosmologists were grappling with a perplexing issue known as the horizon problem. This problem arises from the observation that the cosmic microwave background, CMB, radiation, which is the afterglow of the Big Bang, appears remarkably uniform in all directions. This uniformity is puzzling because the regions of the sky we observe in opposite directions are separated by distances so vast that, according to the standard Big Bang model, they should never have been in causal contact. In other words, there's no way these regions could have exchanged information or reached a state of thermal equilibrium. This is akin to finding two rooms on opposite sides of a vast castle that are both exactly the same temperature, despite never having been connected by any corridor or passageway. To visualize this, imagine the universe as a vast, expanding balloon. Different points on the balloon's surface represent different regions of the sky. The CMB radiation is like the temperature of the balloon's surface. If you measure the temperature at 2 points on opposite sides of the balloon, you find they are the same. However, if the balloon has always been expanding at the rate described by the standard Big Bang model, these 2 points should never have been close enough to influence each other's temperature. This is the essence of the horizon problem. Early proposals of inflationary theory emerged as a potential solution to this conundrum. The idea, pioneered by physicists like Alan Guth, André Linde, and Paul Steinhardt, was that the universe underwent a period of exponential expansion, or inflation, in its earliest moments. This rapid expansion would have stretched any initial inhomogeneities to such an extent that the entire observable universe would have originated from a single, causally connected region. Think of it as taking a small, uniform patch of fabric and stretching it out to cover a vast area. The fabric's uniformity would be preserved across the entire area, even though the individual threads are now too far apart to interact directly. Inflationary theory also elegantly ties into the concept of cosmic inflation, which is the idea that the universe underwent a period of accelerated expansion. During this phase, the universe expanded at an exponential rate, driven by a hypothetical form of energy called the inflating field. This rapid expansion would have smoothed out any irregularities and set the stage for the large-scale structure we observe today. Moreover, quantum fluctuations in the inflating field during this period could have seeded the tiny density variations that eventually gave rise to galaxies and galaxy clusters. This mechanism provides a natural explanation for the observed large-scale structure of the universe and the uniformity of the CMB radiation. Guth's inflationary universe model. The universe, on the largest scales, is remarkably uniform. The cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, shows tiny temperature fluctuations that are almost perfectly evenly distributed. This uniformity presents a puzzle known as the horizon problem. In a universe that's only about 13.8 billion years old, regions of space that are now widely separated should never have been in causal contact. They should not have had time to reach thermal equilibrium, yet they appear to be at the same temperature. This is like having 2 pots of water on a stove that are too far apart to exchange heat, yet they somehow reach the same temperature. To resolve this, cosmologist Alan Guth proposed the inflationary universe model. The idea is that the universe underwent a period of exponential expansion, doubling in size many times over in a fraction of a second. This rapid expansion would have stretched any initial irregularities in the universe to scales larger than the observable universe today. It would also have stretched causal horizons apart, explaining why different regions of the universe appear to be in thermal equilibrium despite never having been in contact. Think of it like a balloon being inflated. As the balloon expands, any dots drawn on its surface move away from each other, but the space between them is stretched, too. This process can make widely separated dots appear uniform, even if they were never directly connected. Guth's model also provides an explanation for the flatness of the universe. Measurements of the CMB show that the geometry of the universe is very close to flat, meaning that the sum of the angles in a triangle is 180 degrees. In the early universe, there was a delicate balance between the density of matter and the rate of expansion. Any slight deviation would have led to a universe that was either closed, positively curved, or open, negatively curved. Inflation explains this fine-tuning by stretching the universe to the point where any initial curvature is diluted to negligible levels. It's like taking a small, curved piece of paper and stretching it out to the size of a room. The curvature becomes so small that it's effectively flat. Moreover, inflation provides a mechanism for generating the seeds of cosmic structure. Quantum fluctuations during the inflationary epoch would have been stretched to macroscopic scales, providing the initial density perturbations that eventually grew into galaxies and galaxy clusters. This is supported by observations of the CMB, which show a pattern of temperature fluctuations that matches the predictions of inflation. The model also explains why the universe is so large and why the CMB is so uniform. It's a testament to the power of a simple idea, that the universe underwent a period of rapid expansion in its earliest moments. This expansion smoothed out any initial irregularities, set the stage for the formation of structure, and left us with the universe we see today. The role of false vacuum energy. The universe, in its earliest moments, was a hot, dense soup of particles and radiation. As it expanded and cooled, these particles began to combine and form the first atoms. However, this process posed a significant challenge: the uniformity of the cosmic microwave background, CMB, radiation. This uniformity is puzzling because different regions of the universe that appear similar today were not in causal contact with each other in the early universe. This is the essence of the horizon problem. To understand this, picture the universe as a vast canvas. If you take 2 points on this canvas that are far apart, they should look different because they haven't interacted. Yet, the CMB shows that these points look eerily similar. This suggests that something must have smoothed out these differences, and that something is cosmic inflation. Cosmic inflation proposes that the universe underwent a period of exponential expansion in its first tiny fraction of a second. During this time, quantum fluctuations were stretched out to cosmic scales, seeding the large-scale structure of the universe. But what drove this rapid expansion? The leading candidate is false vacuum energy. Think of the vacuum as the lowest possible energy state of the universe. However, in the early universe, the vacuum might have been in a false state, higher in energy than the true vacuum. This false vacuum energy could have provided the repulsive gravity needed to drive inflation. It's like a ball perched on a hill. It's not in the lowest energy state, but it's stable until a small perturbation knocks it down to the valley below. Similarly, the false vacuum was stable until a quantum fluctuation triggered the phase transition to the true vacuum, ending inflation. The role of false vacuum energy in cosmic inflation is crucial. It explains not only the horizon problem, but also the flatness problem and the magnetic monopole problem. The energy density of the false vacuum is constant, providing a repulsive force that drives the exponential expansion. As the universe inflates, the energy of the false vacuum is converted into particles and radiation, reheating the universe and setting the stage for the hot Big Bang. This transition from false vacuum to true vacuum is a phase transition, much like water turning into ice. The energy released in this transition can create particles, reheating the universe. The specific details of this phase transition depend on the physics of the false vacuum, which is still an active area of research. Visualizing this process can be challenging, but think of it like a balloon being inflated rapidly. The surface of the balloon represents the universe. As the balloon inflates, any 2 points on the surface move apart rapidly. If you mark 2 points far apart on the balloon, they were once close together before inflation. This is analogous to how regions of the universe that are now far apart were once in causal contact. The false vacuum energy is like the air being pumped into the balloon, driving the rapid expansion. When the balloon pops, the air rushes out, reheating the surface. Similarly, the end of inflation sees the false vacuum energy decaying into particles and radiation, reheating the universe. This process sets the initial conditions for the universe we observe today, with its uniform CMB and large-scale structure. Exponential expansion during inflation. The universe, in its earliest moments, was a place of rapid and dramatic change. This period, known as cosmic inflation, was a time of exponential expansion. Picture a tiny speck, smaller than a single atom, growing at an astonishing rate. In a fraction of a second, it expanded to a size larger than a galaxy. This exponential growth is a key feature of cosmic inflation. It's like taking a tiny balloon and inflating it to the size of a planet in the blink of an eye. This rapid expansion helps to explain why the universe appears so uniform on large scales. It's as if the entire cosmos was once so small that it could reach thermal equilibrium, leading to the uniform temperature we observe today. The exponential expansion during inflation can be visualized using the concept of an exponential function. Imagine a graph where the y-axis represents the size of the universe and the x-axis represents time. In the early moments, the graph is flat. Then, suddenly, it shoots upwards almost vertically. This steep curve represents the exponential growth during inflation. The universe's size doubles, then doubles again and again and again in an incredibly short period. This rapid doubling is what makes the expansion exponential. It's like compound interest on a cosmic scale, where the amount grows by a fixed proportion over equal increments of time. The horizon problem is a key issue that cosmic inflation helps to resolve. The problem arises because the universe appears uniform on scales that are too large for any causal interaction to have occurred since the Big Bang. Think of it like this. If you look at 2 points in the sky that are far apart, they appear to have the same temperature. But in the time since the Big Bang, there hasn't been enough time for these 2 points to exchange energy or information. It's like seeing 2 people on opposite sides of a vast ocean and noticing they're wearing the same shirt, even though they've never met. Cosmic inflation explains this by proposing that these points were once in close proximity before the universe underwent its rapid expansion. They had time to reach thermal equilibrium, and then inflation stretched them apart. It's like taking a small, uniform patch of fabric and stretching it to cover a large area. The fabric remains uniform because it was once a single, connected piece. Solving the horizon problem with inflation. The universe, as we observe it today, presents a puzzling uniformity. The cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, exhibits remarkable uniformity across the entire sky. This uniformity is perplexing because the regions of the sky we see were not in causal contact with each other in the early universe. This is the essence of the horizon problem. In simpler terms, it's like seeing 2 distant mountains that look identical, but there's no way they could have communicated or interacted to become so similar. This lack of interaction poses a challenge to our understanding of the early universe. To visualize the horizon problem, picture the universe as a vast expanse of space. Light and other information can only travel at the speed of light. In the early universe, the distance that light could travel, the particle horizon, was much smaller than the size of the observable universe today. This means that different regions of the universe were causally disconnected. They couldn't exchange information or influence each other. Yet, these regions appear remarkably similar. It's as if you could see 2 distant galaxies that look identical, but there's no way they could have interacted to become so alike. This uniformity suggests that something must have happened to ensure these regions had the same properties, despite being out of causal contact. Cosmic inflation provides an elegant solution to the horizon problem. Inflation is a theory that proposes the universe underwent a period of exponential expansion in its earliest moments. During this rapid expansion, any region of space that we can observe today was once incredibly small, much smaller than the particle horizon. This means that all parts of the observable universe were once in causal contact. They could exchange information and reach a state of thermal equilibrium. It's like taking a tiny, uniform patch of space and stretching it out to encompass the entire observable universe. This rapid expansion ensures that the uniformity we observe in the CMB radiation is a relic of the early, uniform conditions of the universe. Moreover, inflation explains why the universe appears so uniform on large scales. As the universe expanded exponentially, any irregularities or anisotropies were stretched out and smoothed out. This process is often compared to taking a crumpled piece of paper and stretching it out. The crumples become less noticeable as the paper expands. In the context of the universe, this means that any initial irregularities were smoothed out during the inflationary period, leading to the uniform conditions we observe today. This explanation ties together the horizon problem and the uniformity of the CMB radiation, providing a coherent picture of the early universe. Homogeneity and isotropy in an inflating universe. The universe, on the largest scales, appears remarkably uniform. This uniformity is described by two key properties: homogeneity and isotropy. Homogeneity means that the universe looks the same in all places. No particular region stands out as special. Isotropy means that the universe looks the same in all directions. These properties are crucial for our understanding of the cosmos. However, they also pose a significant challenge, known as the horizon problem. The observable universe is so vast that different regions should not have had time to exchange information or reach thermal equilibrium, given the age of the universe. This is where cosmic inflation steps in to provide an explanation. Cosmic inflation is a theory that proposes the universe underwent a period of exponential expansion in its earliest moments. During this rapid expansion, quantum fluctuations were stretched out to cosmic scales, seeding the large-scale structure we observe today. This process can account for the homogeneity and isotropy of the universe. As the universe inflated, any initial irregularities were smoothed out, much like how stretching a crumpled piece of paper would make it appear smoother. This exponential growth ensured that the entire observable universe originated from a tiny, causally connected region, resolving the horizon problem. The uniformity we observe is a direct consequence of this rapid expansion. Visualizing this can be helpful. Imagine a balloon being inflated. As the balloon expands, any dots on its surface move away from each other, but the relative distances between them remain uniform. Similarly, during cosmic inflation, space itself was stretched, carrying along any matter and energy within it. This stretching ensured that the universe became homogeneous and isotropic. The cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, provides strong evidence for this. The CMB is incredibly uniform, with only tiny fluctuations. These fluctuations are exactly what we would expect if the universe underwent a period of inflation, amplifying quantum fluctuations to cosmic scales. Moreover, inflation also explains why the universe appears flat on the largest scales. In an inflating universe, the curvature of space is diluted, making the universe appear flat to us. This is consistent with observations, which show that the geometry of the universe is very close to flat. The theory of cosmic inflation elegantly ties together these diverse observations, providing a comprehensive framework for understanding the early universe. It explains homogeneity, isotropy, the flatness of the universe, and the origin of cosmic structure. While there are still many open questions and areas of active research, inflation remains a cornerstone of modern cosmology. Quantum fluctuations during inflation. In the vast expanse of the cosmos, the universe presents a remarkably uniform appearance. This uniformity, however, poses a significant challenge known as the horizon problem. The issue arises because the observable universe is so large that different regions should not have had time to exchange energy or information, and thus should not have reached a state of thermal equilibrium. Yet they have. This conundrum is neatly resolved by the theory of cosmic inflation, which posits that the universe underwent a period of exponential expansion in its earliest moments. During this rapid expansion, regions that are now causally disconnected were once in close proximity, allowing them to reach a state of thermal equilibrium. Quantum fluctuations during inflation play a crucial role in this scenario. As the universe inflated, quantum fluctuations in the inflaton field, the hypothetical field responsible for driving inflation, were stretched to macroscopic scales. These fluctuations imparted tiny density variations in the otherwise uniform early universe. These density variations, in turn, served as the seeds for the large-scale structure we observe today, including galaxies and galaxy clusters. The pattern of these fluctuations, imprinted in the cosmic microwave background, CMB, radiation, provides a snapshot of the universe's infancy and offers a window into the physics of inflation. The connection between quantum fluctuations and cosmic inflation is profound. Inflationary theory predicts that these fluctuations should follow a specific statistical pattern, often described as a nearly scale-invariant spectrum. Observations of the CMB, such as those made by the Planck satellite, have confirmed this prediction with remarkable precision. The fluctuations are not only a testament to the quantum nature of the early universe, but also a direct consequence of the rapid expansion during inflation. This expansion stretched quantum fluctuations to cosmic scales, imprinting them on the fabric of the universe. The detailed analysis of these fluctuations provides a powerful tool for probing the physics of the early universe and the mechanisms driving inflation. Moreover, the study of quantum fluctuations during inflation offers insights into the fundamental nature of the universe. The fluctuations are a manifestation of the uncertainty principle, which states that certain pairs of physical properties, like position and momentum, cannot both be precisely known. In the context of inflation, this principle leads to inevitable quantum fluctuations in the inflating field. These fluctuations, when stretched to cosmic scales, become the seeds for the large-scale structure of the universe. The detailed study of these fluctuations not only sheds light on the early universe, but also provides a deeper understanding of the quantum nature of reality. The interplay between quantum mechanics and cosmology in this context highlights the profound connections between the smallest and largest scales in the universe, generating primordial density perturbations. The universe, as we observe it today, is filled with structures, galaxies, clusters, and superclusters. These structures didn't form spontaneously. They evolved from tiny fluctuations in the early universe's density. These fluctuations, known as primordial density perturbations, are crucial for understanding the large-scale structure of the cosmos. They are minute variations in the density of the early universe, seeds from which galaxies and other cosmic structures grew. Think of them as tiny ripples on the surface of an otherwise smooth pond. Over time, these ripples grow and evolve into the complex patterns we see today. Cosmic inflation, a period of exponential expansion in the early universe, plays a pivotal role in generating these primordial density perturbations. During inflation, quantum fluctuations in the inflating field, the hypothetical field responsible for driving inflation, created tiny density variations. These fluctuations were then stretched to cosmic scales by the rapid expansion of the universe. The exact nature of these perturbations depends on the specifics of the inflationary model. Some models predict that the perturbations are adiabatic, meaning that the fluctuations in density are accompanied by fluctuations in temperature. Others suggest that the perturbations are isocurvature, where the fluctuations occur in the relative numbers of different particle species without affecting the overall density. The primordial density perturbations are characterized by their amplitude and spectral index. The amplitude measures the size of the fluctuations, while the spectral index describes how the amplitude varies with scale. Observations of the cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, provide a wealth of information about these perturbations. The CMB anisotropies, or temperature variations, are direct imprints of the primordial density perturbations. By analyzing these anisotropies, scientists can infer the properties of the early universe and test different inflationary models. The Planck satellite, for instance, has provided high-precision measurements of the CMB, offering insights into the nature of the primordial perturbations. Understanding the generation of primordial density perturbations is not just an academic exercise. It has profound implications for our understanding of the universe's evolution. These perturbations are the seeds from which all cosmic structures grew. Without them, the universe would be a featureless expanse, devoid of the galaxies, stars, and planets that make up the cosmos we see today. Moreover, studying these perturbations allows us to probe the physics of the early universe, including the nature of inflation and the fundamental laws governing the cosmos. It's a window into the very beginning of time, offering clues about the universe's origins and its ultimate fate. The end of inflation, reheating. Cosmic inflation is a theory that attempts to explain the rapid expansion of the universe fractions of a second after the Big Bang. It posits that the universe underwent a period of exponential growth, smoothing out any irregularities and making the universe appear uniform on large scales. This uniformity, however, presents a puzzle known as the horizon problem. The horizon problem questions why different regions of the universe, which are so far apart that they should never have been in causal contact, exhibit the same temperature and other physical properties. Inflation offers a solution by suggesting that these regions were once in contact before being pushed apart by the rapid expansion. The end of inflation marks a critical transition in the early universe's evolution. This phase, known as reheating, is when the universe's energy, which had been driving the rapid expansion, is converted back into particles and radiation. Picture a balloon being inflated rapidly and then suddenly stopping. The energy used to inflate it doesn't just disappear. It's transferred into the balloon's material, heating it up. Similarly, during reheating, the energy of the inflatant field, the hypothetical field responsible for inflation, decays into particles, reheating the universe and setting the stage for the hot, dense state described by the Big Bang theory. Reheating is not an instantaneous process. It involves complex interactions and decays of the inflatant field. The inflatant field oscillates around its minimum energy state, much like a pendulum swinging back and forth. These oscillations create particles, and the universe gradually fills with a hot plasma of quarks, leptons, and their antiparticles. This process is crucial because it establishes the initial conditions for the hot Big Bang phase. Without reheating, the universe would have been too cold and empty to form the structures we see today. The details of reheating are still not fully understood. Different models of inflation predict different reheating scenarios. Some suggest a relatively smooth transition, while others propose a more violent, turbulent phase. Observational data, such as the cosmic microwave background radiation, can provide clues about reheating. By studying the patterns and fluctuations in this radiation, scientists can infer the conditions of the early universe and test different reheating models. This ongoing research is vital for understanding the fundamental physics of the early universe and the nature of cosmic inflation. Transition from inflation to the standard Big Bang. The universe, in its earliest moments, was a place of rapid expansion and extreme conditions. Cosmic inflation, a theory that explains the exponential growth of the universe, sets the stage for the standard Big Bang model. During inflation, the universe expanded faster than the speed of light, smoothing out any irregularities and making the universe appear uniform. This period of rapid expansion was driven by a hypothetical field called the inflatant, which dominated the energy density of the universe. The inflatant field decayed, releasing its energy and reheating the universe, marking the transition from inflation to the standard Big Bang. Visualize the transition like a balloon being inflated rapidly and then suddenly stopping. The balloon's surface represents the universe, and the rapid inflation is the exponential expansion. When the inflation stops, the balloon's surface is uniform and smooth, much like the universe after inflation. The reheating phase is akin to the balloon's surface being filled with tiny, evenly distributed dots, representing the particles and energy that filled the universe post-inflation. This uniformity is crucial for understanding the cosmic microwave background, CMB, radiation, the afterglow of the Big Bang that we observe today. The horizon problem, a key issue addressed by cosmic inflation, arises from the observation that different regions of the universe are in thermal equilibrium, meaning they have the same temperature and properties. This is puzzling because these regions are so far apart that they should not have had time to interact or exchange energy, given the age of the universe. Inflation resolves this by proposing that these regions were once in causal contact before the rapid expansion separated them. During inflation, the universe doubled in size many times over, ensuring that any 2 points could have been in contact before inflation pushed them apart. The transition from inflation to the standard Big Bang is not instantaneous. It involves a complex process of reheating, where the energy stored in the inflatant field is converted into particles and radiation. This reheating phase sets the initial conditions for the hot, dense state of the universe described by the Big Bang model. The universe continues to expand and cool, allowing particles to combine and form the first atoms, which eventually lead to the formation of stars, galaxies, and the large-scale structure we observe today. The smooth transition from inflation to the standard Big Bang provides a coherent picture of the early universe, explaining its uniformity, flatness, and the abundance of matter and energy. Evidence supporting cosmic inflation. The universe, as we observe it today, presents a remarkable uniformity. The cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, exhibits tiny temperature fluctuations that are incredibly uniform across the entire sky. This uniformity poses a puzzle known as the horizon problem. In a universe without cosmic inflation, regions of space that are now widely separated would have been causally disconnected, meaning they couldn't have exchanged information or reached thermal equilibrium. This makes their similar temperatures and properties puzzling. Cosmic inflation offers a solution to this problem. It suggests that the universe underwent a period of exponential expansion in its earliest moments. During this rapid expansion, any initial irregularities were stretched out, smoothing the universe to the uniform state we observe today. Inflation also provides a mechanism for generating the slight variations in temperature and density that we see in the CMB. Quantum fluctuations during the inflationary period would have been stretched to cosmic scales, seeding the formation of galaxies and large-scale structures. This prediction aligns well with observations, as the CMB exhibits precisely the kind of fluctuations expected from an inflationary universe. Moreover, the theory of cosmic inflation makes another crucial prediction. The universe should be flat, or very nearly so, on the largest scales. Observations of the CMB have confirmed this prediction, showing that the geometry of the universe is indeed flat to a high degree of precision. One of the most compelling pieces of evidence supporting cosmic inflation comes from the BICEP 2 experiment, which detected a specific pattern of polarization in the CMB known as B modes. These patterns are thought to be imprints of gravitational waves generated during the inflationary epoch. While the initial claims of detection have been subject to debate and further investigation, the search for these primordial gravitational waves continues to be a major focus of cosmological research. If confirmed, they would provide direct evidence of the rapid expansion that occurred during cosmic inflation. Another line of evidence comes from the large-scale structure of the universe. The distribution of galaxies and galaxy clusters can be traced back to the slight density fluctuations in the early universe. The patterns observed in these structures match the predictions made by inflationary models, providing further support for the theory. Additionally, the abundance of light elements, such as hydrogen and helium, in the universe aligns with the predictions of Big Bang nucleosynthesis, which is consistent with the conditions set by cosmic inflation. These multiple lines of evidence, from the CMB to the large-scale structure of the universe, paint a coherent picture that strongly supports the theory of cosmic inflation as the solution to the horizon problem. CMB anisotropies and inflationary predictions. The universe, as we observe it today, presents a puzzling uniformity. The cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, exhibits remarkable uniformity across the sky. This uniformity, however, poses a challenge known as the horizon problem. The issue arises because the regions of the universe that we see in the CMB were not in causal contact with each other in the early universe. In other words, they were too far apart for any interaction or exchange of information to have occurred. This lack of contact makes the observed uniformity puzzling. It's like seeing two distant cities with identical weather patterns, but with no mechanism for the weather to synchronize between them. To visualize this, imagine the universe as a vast, expanding balloon. Different points on the balloon's surface represent different regions of the universe. The CMB radiation is like the color of the balloon's surface. If you look at different points on the balloon, you expect to see slight variations in color, or in this case, temperature. However, the CMB is almost perfectly uniform, with only tiny fluctuations. These tiny fluctuations, known as anisotropies, are crucial for understanding the universe's structure and evolution. They provide a snapshot of the universe when it was just 380 years old, and their pattern encodes information about the universe's composition, geometry, and history. Cosmic inflation, a theory proposed to explain the universe's rapid expansion in its earliest moments, offers a solution to the horizon problem. According to this theory, the universe underwent a period of exponential growth, doubling in size many times over in a fraction of a second. This rapid expansion would have stretched any initial non-uniformities, smoothing them out and making the universe appear uniform. Moreover, quantum fluctuations during this inflationary period would have seeded the tiny anisotropies we observe in the CMB. These fluctuations would have been stretched to cosmic scales, providing the initial density variations that eventually led to the formation of galaxies and other large-scale structures. The predictions of cosmic inflation about CMB anisotropies have been remarkably successful. The theory predicts that the anisotropies should follow a specific pattern, with the power spectrum of the fluctuations exhibiting a characteristic shape. This shape is determined by the nature of the inflationary potential and the number of E-folds of expansion. Observations of the CMB, such as those from the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, have confirmed these predictions with high precision. The data shows a nearly scale-invariant spectrum of fluctuations, with a slight tilt that is consistent with the predictions of simple inflationary models. This tilt provides valuable information about the energy scale of inflation and the dynamics of the early universe. Large-scale structure formation. The universe, as we observe it today, is a vast cosmic web of galaxies, galaxy clusters, and superclusters. This large-scale structure is not random. It's a complex network of filaments and voids, a testament to the intricate dance of gravity and the initial conditions of the universe. The formation of this structure is a fascinating process that begins with tiny quantum fluctuations in the early universe. These fluctuations, magnified by cosmic inflation, served as seeds for the large-scale structures we see today. Cosmic inflation, a period of exponential expansion in the early universe, stretched these quantum fluctuations to cosmic scales, creating density variations that would eventually grow into the cosmic web. Picture this. The early universe is like a vast, featureless canvas. Quantum fluctuations are like the first brushstrokes, creating tiny variations in density. Cosmic inflation then stretches this canvas, making these variations larger and more pronounced. Over time, gravity takes over, pulling matter into the denser regions and creating the filaments and voids of the cosmic web. This process is not uniform. It's a complex interplay of forces that results in the intricate structure we observe today. The filaments, composed of dark matter and galaxies, are the highways of the cosmos, connecting the massive galaxy clusters and superclusters. The voids, on the other hand, are the vast, empty spaces between these filaments. The horizon problem, a term coined to describe the uniformity of the cosmic microwave background, CMB, radiation, is closely linked to cosmic inflation and large-scale structure formation. The CMB is the afterglow of the Big Bang, a snapshot of the universe when it was just 380 years old. The uniformity of the CMB suggests that different regions of the early universe were in thermal equilibrium, despite being separated by distances that light could not have traversed in the time since the Big Bang. This is the horizon problem. Cosmic inflation provides a solution to this problem. During inflation, the universe expanded so rapidly that regions that were once in causal contact were stretched apart. This explains the uniformity of the CMB and sets the initial conditions for the formation of the large-scale structure. The process of large-scale structure formation is not yet complete. The universe is still evolving, with gravity continuing to pull matter into the denser regions of the cosmic web. This ongoing process is shaped by the nature of dark matter and dark energy, two of the most mysterious components of the universe. Dark matter, which does not interact with light, provides the gravitational scaffolding for the cosmic web. Dark energy, on the other hand, is driving the accelerated expansion of the universe, a process that may eventually tear the cosmic web apart. Understanding the nature of these components is crucial for unraveling the mysteries of large-scale structure formation and the ultimate fate of the universe. Inflation and the flatness problem. The universe, on the largest scales, appears remarkably uniform. The cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, shows tiny temperature fluctuations that are nearly the same everywhere we look. This uniformity presents a puzzle known as the horizon problem. In a universe without cosmic inflation, regions of space that are now causally disconnected, meaning they could not have exchanged signals or influences, would have no reason to have the same temperature or properties. This is akin to having two rooms on opposite sides of a vast, unconnected building maintaining the exact same temperature without any physical connection. Cosmic inflation, a period of exponential expansion in the early universe, offers a solution. During inflation, the universe expanded faster than the speed of light, causing initially small, causally connected regions to become stretched out and disconnected. This rapid expansion smoothed out any irregularities, leading to the uniform universe we observe today. Think of it like taking a small, crumpled piece of paper and stretching it out to a huge size. The crumples become so spread out that the paper appears smooth and uniform. This process also explains why the universe appears flat. In an inflating universe, the geometry of space is stretched to the point where it is indistinguishable from flat, even if it is slightly curved on the largest scales. The flatness problem is closely linked to the horizon problem. Without inflation, the universe would have to be finely tuned to an incredible degree to appear as flat as it does. Any initial curvature would have grown over time, leading to a universe that is either closed, finite and bound to recollapse, or open, infinite and expanding forever. Inflation, however, ensures that the universe is flat to an extraordinary degree. It's like balancing a needle on its tip. Without inflation, the universe would have had to be balanced just right to remain flat, which is highly improbable. Inflation provides a natural mechanism to explain this flatness, making it a cornerstone of modern cosmology. Moreover, inflation's role in solving the flatness problem is not just a theoretical nicety. It has observable consequences. The tiny fluctuations in the CMB that we detect today are the seeds of the large-scale structure we see in the universe. These fluctuations are consistent with the predictions of inflationary models, providing strong evidence for the theory. The uniformity and flatness of the universe are not just coincidences, but are natural outcomes of a period of rapid expansion in the early universe. This connection between the horizon problem, the flatness problem, and cosmic inflation underscores the deep interplay between different aspects of cosmology and the power of inflation to explain the universe's large-scale properties. Inflationary models and their predictions. The universe, as we observe it today, presents a uniformity that is both striking and perplexing. The cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, exhibits remarkable uniformity across the sky. This uniformity, however, poses a challenge known as the horizon problem. In a universe without cosmic inflation, regions of space that are now causally disconnected, meaning they could not have exchanged information or thermal equilibrium, should exhibit different temperatures. Yet, the CMB shows a near-perfect uniformity, with temperature variations of only about 1 part in 100, 0. This suggests that these regions must have been in thermal equilibrium at some point, but the standard Big Bang model does not provide a mechanism for this to occur. Cosmic inflation offers a solution to the horizon problem. Inflation posits that the early universe underwent a period of exponential expansion, stretching quantum fluctuations to cosmic scales. This rapid expansion would have ensured that all regions of the observable universe today were once in causal contact, allowing them to reach thermal equilibrium. The theory of cosmic inflation is not a single model but a family of models, each with its own predictions and mechanisms. These models generally share the idea that a scalar field, often referred to as the inflaton, drove the rapid expansion of the universe. The specific details of the inflaton field, its potential energy landscape, and the duration of inflation vary between models. One of the most well-known inflationary models is the power law inflation model, which predicts a specific form for the primordial power spectrum of density fluctuations. This model suggests that the universe underwent a period of exponential expansion driven by a scalar field with an exponential potential. Another prominent model is the chaotic inflation model, which posits that inflation can occur in a wide range of potential energy landscapes, including quadratic and quartic potentials. Each of these models makes distinct predictions about the statistical properties of the CMB, such as the spectral index of primordial fluctuations and the amplitude of gravitational waves. Observations of the CMB by experiments like the Planck satellite have provided constraints on these models, favoring those with a relatively flat primordial power spectrum. The predictions of inflationary models extend beyond the CMB. They also make specific predictions about the large-scale structure of the universe, the abundance of primordial black holes, and the properties of gravitational waves. For instance, some models predict the existence of a stochastic background of gravitational waves, which could be detected by future experiments. Additionally, inflationary models can explain the observed lack of magnetic monopoles and other topological defects, as these would have been diluted during the rapid expansion. The interplay between theoretical predictions and observational data continues to refine our understanding of cosmic inflation and its role in shaping the universe we observe today. Challenges and criticisms of inflationary theory. Cosmic inflation, a theory proposing that the universe underwent exponential expansion in its earliest moments, has been instrumental in explaining the uniformity of the cosmic microwave background, SMB, radiation, a relic from the early universe. This uniformity presents a puzzle known as the horizon problem. Why does the CMB look the same in opposite directions of the sky, even though these regions were once too far apart to have interacted or exchanged information? Inflation resolves this by suggesting that these regions were once in causal contact before being stretched apart during the rapid expansion. However, despite its explanatory power, inflationary theory faces several challenges and criticisms. One significant challenge is the lack of direct experimental evidence. While inflation makes several testable predictions, such as the specific pattern of temperature fluctuations in the CMB, these are indirect confirmations. Scientists have yet to detect primordial gravitational waves, which are a key prediction of inflation and would provide direct evidence of the rapid expansion. The absence of such detection leaves room for alternative theories that could also explain the observed uniformity of the CMB without invoking inflation. Moreover, the theory relies on hypothetical particles and fields, like the inflaton, which have not been observed. This makes it difficult to falsify the theory, a crucial aspect of the scientific method. Another criticism revolves around the fine-tuning problem. Inflation requires specific initial conditions and a precise balance of energy to work. For instance, the potential energy of the inflaton field must be finely tuned to drive the rapid expansion without leading to a catastrophic outcome, like a runaway expansion or a collapse. This fine-tuning raises questions about the naturalness of the theory. Some critics argue that inflation is not a complete theory, but rather a framework that needs more detailed physics to explain these initial conditions. Additionally, the theory allows for a vast landscape of possible initial conditions, leading to an array of potential universes with different properties. This multiverse interpretation, while intriguing, is currently untestable and thus controversial. Furthermore, inflation faces challenges from alternative theories that also aim to explain the horizon problem. For example, some theories propose that the universe underwent a phase of rapid acceleration due to a different mechanism, like a modification of general relativity. Others suggest that the universe is not as uniform as it appears, and the observed uniformity is a result of our limited observational capabilities. These alternatives, while often less developed than inflation, highlight the need for more robust evidence to distinguish between competing theories. Until such evidence is found, the debate surrounding inflation and its criticisms will likely continue. Alternative solutions to the horizon problem. The universe, as we observe it, presents a puzzling uniformity. The cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, shows remarkable uniformity across the entire sky. This uniformity is perplexing because the regions of the sky we see were not in causal contact with each other in the early universe. This is the essence of the horizon problem. In simpler terms, it's like seeing two distant cities with identical weather conditions, but there's no mechanism for them to influence each other directly. The most widely accepted solution to this problem is cosmic inflation, a rapid expansion of the universe in its infancy. However, alternative solutions have been proposed, each with its own unique perspective. One alternative approach involves modifications to the initial conditions of the universe. Instead of assuming that the universe started with a Big Bang singularity, some theories suggest that it began with a Big Bounce, or a quantum gravitational state. In these scenarios, the universe could have undergone a previous phase of contraction before the Big Bang, allowing different regions to exchange information and reach a state of thermal equilibrium. This would mean that the uniformity we observe in the CMB is a remnant of this pre-Big Bang phase. While these ideas are speculative, they offer a different angle on the horizon problem, one that doesn't necessarily require a period of cosmic inflation. Another intriguing alternative is the ekpyrotic universe model. This theory suggests that our universe is a four-dimensional brane, a membrane, floating in a higher dimensional space. The uniformity of the CMB could be explained by collisions between our brane and a parallel brane. These collisions would create a hot, dense state that could then expand and cool, giving rise to the uniform conditions we observe. This model is part of a broader framework known as string theory landscape, which posits a vast number of possible universes, each with its own set of physical laws. While the ekpyrotic model is still a work in progress, it offers a creative and unconventional solution to the horizon problem. Lastly, some researchers have explored the possibility that the uniformity of the CMB is not a fundamental feature of the universe, but rather a result of our specific vantage point. In this view, the universe could be highly inhomogeneous on the largest scales, but we happen to live in a region that appears uniform. This idea is often linked to the concept of the multiverse, where our universe is just one among an infinite number of universes, each with its own unique properties. While this solution is philosophically appealing, it is challenging to test experimentally. Nevertheless, it serves as a reminder that the horizon problem is far from resolved and that our understanding of the universe is still evolving. Comparing inflation with other models. The horizon problem in cosmology refers to the observation that the universe appears remarkably uniform on large scales, despite the fact that regions of the observable universe that are now far apart were never in causal contact with each other. This uniformity suggests that these regions must have been in thermal equilibrium at some point in the past, but the standard Big Bang model does not provide a mechanism for this to happen. This is where cosmic inflation comes into play. Inflation proposes that the universe underwent a period of exponential expansion in its earliest moments. This rapid expansion would have stretched any initial inhomogeneities to scales larger than the observable universe, effectively smoothing out any irregularities. As a result, the universe would appear uniform on large scales, resolving the horizon problem. Inflation is not the only model that attempts to address the horizon problem. Other models, such as the ekpyrotic universe or the string gas cosmology, offer alternative explanations. The ekpyrotic universe, for instance, suggests that the universe's uniformity arises from a collision between two three-dimensional worlds, branes, in a higher dimensional space. This collision would create a hot, dense state that could explain the observed uniformity. String gas cosmology, on the other hand, posits that the early universe was filled with a gas of fundamental strings. The interactions of these strings would lead to a state of thermal equilibrium, similar to what is observed today. Comparing inflation with these other models reveals both strengths and weaknesses. Inflation is favored by many cosmologists because it not only addresses the horizon problem, but also provides a natural explanation for the flatness problem and generates a spectrum of primordial density fluctuations that match observations. However, inflation requires fine-tuning of the initial conditions and the parameters of the inflationary potential. The ekpyrotic universe and string gas cosmology, while elegant in their own right, have not yet been as successful in matching observational data. For example, the ekpyrotic model struggles to produce the correct spectrum of primordial fluctuations, and string gas cosmology has difficulty explaining the observed large-scale structure of the universe. Despite these challenges, the search for a comprehensive model of the early universe continues. Each model offers unique insights and raises important questions. Inflation remains the most widely accepted theory due to its predictive power and consistency with observations. Yet, the exploration of alternative models is crucial for a deeper understanding of the cosmos. As new data from experiments like the Planck satellite and the Large Hadron Collider become available, cosmologists will be better equipped to distinguish between these models and refine our understanding of the universe's origins. Observational tests of inflationary cosmology. The universe, as we observe it today, presents a remarkable uniformity. The cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, exhibits tiny temperature fluctuations that are nearly identical across vast distances. This uniformity, however, poses a puzzle known as the horizon problem. In a universe without inflation, regions of space that are now causally disconnected, meaning they could not have exchanged signals or interacted in any way, should exhibit significant temperature differences. Yet, they don't. This observation suggests that these regions must have been in thermal equilibrium at some point, implying a mechanism that could bring them into contact. Cosmic inflation offers a compelling solution to the horizon problem. Inflation posits that the early universe underwent a period of exponential expansion, stretching quantum fluctuations to cosmic scales. During this rapid expansion, the entire observable universe was once contained within a single causal horizon, allowing different regions to reach thermal equilibrium. This exponential growth means that even regions now far apart were once close enough to interact, explaining the uniformity we observe in the CMB. The theory of cosmic inflation thus provides a natural explanation for the horizon problem, linking the uniformity of the early universe to the rapid expansion that occurred during its infancy. Observational tests of inflationary cosmology aim to validate this theoretical framework. One key test involves measuring the statistical properties of the CMB. Inflation predicts that the initial density fluctuations, which seeded the formation of galaxies and large-scale structures, should follow a specific pattern known as a Gaussian distribution. Observations from satellites like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have confirmed this prediction, providing strong support for inflation. Additionally, the CMB data reveals a slight deviation from perfect uniformity, known as anisotropy, which matches the predictions of inflationary models. These anisotropies are crucial as they provide insights into the initial conditions of the universe and the physics of the early universe. Another critical test of inflationary cosmology is the search for primordial gravitational waves. These waves, if detected, would provide direct evidence of the rapid expansion during inflation. The gravitational waves would leave a distinctive imprint on the polarization of the CMB, a pattern known as B-mode polarization. While current observations have not yet detected these primordial gravitational waves, ongoing and future experiments, such as the BICEP array and the LightBird satellite, are designed to search for this signal with unprecedented sensitivity. The detection of primordial gravitational waves would not only confirm inflation, but also provide valuable information about the energy scale of inflation and the physics of the very early universe. Future experiments and probes. The horizon problem presents a fascinating puzzle in cosmology. It arises from the observation that different regions of the cosmos, which should never have been in causal contact due to the finite speed of light and the age of the universe, exhibit remarkably similar properties, such as temperature and density. This uniformity suggests that these regions must have been in thermal equilibrium at some point, but the standard Big Bang model struggles to explain how this could have happened. Enter cosmic inflation, a theory that proposes a period of exponential expansion in the early universe. This rapid expansion would have stretched any initial inhomogeneities to such an extent that the universe would appear uniform on large scales, providing a neat solution to the horizon problem. However, while inflation is widely accepted, it remains a theoretical construct. To validate it, scientists are turning to future experiments and probes. One of the most promising avenues for probing cosmic inflation is the study of the cosmic microwave background, CMB, radiation. The CMB is the afterglow of the Big Bang, and its properties can reveal a wealth of information about the early universe. Future missions, such as the LightBird satellite, aim to measure the polarization of the CMB with unprecedented precision. Polarization patterns can provide clues about the gravitational waves generated during the inflationary epoch. These primordial gravitational waves would leave a distinctive imprint on the CMB, offering a direct test of inflationary models. By analyzing these patterns, scientists hope to confirm the existence of cosmic inflation and gain insights into the energy scale and dynamics of the inflationary period. Ground-based experiments are also playing a crucial role in this quest. The Simons Observatory, currently under construction in the Atacama Desert in Chile, will feature an array of telescopes designed to study the CMB. With its advanced instrumentation, it will be able to detect faint signals from the early universe, including those associated with inflationary gravitational waves. Similarly, the BICEP array at the South Pole is already making strides in this area. By combining data from these ground-based observatories with that from space-based missions, scientists can cross-verify their findings and build a more comprehensive picture of the early universe. These experiments are not just about confirming inflation. They are about understanding the fundamental physics that govern the universe's birth. In addition to CMB studies, future probes of cosmic inflation may come from large-scale galaxy surveys. Projects like the Dark Energy Spectroscopic Instrument, DESI, and the Euclid Space Telescope aim to map the distribution of galaxies and dark matter across the universe. These maps can reveal the imprint of primordial fluctuations, which were seeded during the inflationary epoch. By analyzing the statistical properties of these fluctuations, scientists can test different inflationary models and constrain their parameters. For instance, the shape and amplitude of the primordial power spectrum can provide insights into the potential energy landscape that drove inflation. These galaxy surveys, combined with CMB data, offer a multifaceted approach to probing the early universe and unraveling the mysteries of cosmic inflation. Theoretical developments in inflationary cosmology. Cosmic inflation is a theory that attempts to explain the rapid expansion of the universe in its earliest moments. It posits that the universe underwent a period of exponential growth, driven by a hypothetical field called the inflaton. This field would have caused the universe to expand faster than the speed of light, smoothing out any irregularities and making the universe appear uniform on large scales. The theory of cosmic inflation was first proposed in the late 1970s and early 1980s, and it has since become a cornerstone of modern cosmology. It provides a natural explanation for several observed features of the universe, such as its homogeneity, isotropy, and flatness. One of the key theoretical developments in inflationary cosmology is the idea of eternal inflation. This concept suggests that inflation is not a one-time event, but rather a process that is ongoing and eternal. In this scenario, our universe is just one of many bubble universes that are constantly being created by eternal inflation. Each bubble universe has its own set of physical constants and laws of nature, which can differ from those in other universes. This idea has profound implications for our understanding of the universe and our place in it. It suggests that we may be just one of many universes, each with its own unique properties and history. Another important development in inflationary cosmology is the idea of reheating. This process occurs at the end of inflation, when the inflaton field decays into particles and radiation. This reheating process is thought to have created the hot, dense state of the early universe that is described by the Big Bang Theory. The details of reheating are still not fully understood, but it is an active area of research in cosmology. Understanding reheating is crucial for connecting the physics of inflation with the observed properties of the universe today. Theoretical developments in inflationary cosmology have also led to new insights into the nature of dark matter and dark energy. These mysterious substances make up the majority of the matter and energy in the universe, but their exact nature is still unknown. Inflationary cosmology provides a framework for studying these substances and their effects on the evolution of the universe. For example, some theories suggest that dark matter may have been created during the reheating process, while others suggest that dark energy may be a remnant of the inflaton field. These ideas are still speculative, but they highlight the potential of inflationary cosmology to shed light on some of the deepest mysteries of the universe. Implications for particle physics and quantum gravity. The universe, in its earliest moments, presented a puzzle that has baffled cosmologists for decades. The Horizon Problem, a conundrum arising from the uniformity of the cosmic microwave background, CMB, radiation, challenges our understanding of the cosmos. The CMB, a relic from the early universe, exhibits remarkable uniformity across the sky, with a temperature that is nearly identical in all directions. This uniformity is puzzling because different regions of the sky were not in causal contact with each other in the early universe. In other words, These regions were too far apart for any interaction or exchange of information to have occurred, yet they exhibit the same temperature. This is akin to having two rooms on opposite sides of a vast, empty building that somehow have the exact same temperature without any means of heat transfer. The horizon problem thus raises questions about how these regions could have reached such a similar state without direct interaction. Cosmic inflation, a theory proposed to resolve the horizon problem, suggests that the early universe underwent a period of exponential expansion. During this phase, the universe expanded faster than the speed of light, causing regions that were once in causal contact to become separated. This rapid expansion would have stretched any initial inhomogeneities to such an extent that they became undetectable, resulting in the uniform CMB we observe today. Inflation effectively ironed out the wrinkles in the fabric of space-time, creating the smooth, uniform universe we see. This theory not only addresses the horizon problem, but also provides explanations for other cosmological observations, such as the flatness of the universe and the absence of magnetic monopoles. The implications of cosmic inflation for particle physics and quantum gravity are profound. Inflationary models often rely on scalar fields, such as the inflaton, which drive the exponential expansion of the universe. These fields are hypothetical particles that have not yet been observed, but are predicted by certain particle physics models. The study of inflation thus provides a unique opportunity to probe the physics of these scalar fields and their interactions. Moreover, the extreme conditions of the early universe, where quantum gravity effects are expected to play a significant role, offer a testing ground for theories that aim to unify quantum mechanics and general relativity. For instance, some models of quantum gravity, such as string theory and loop quantum gravity, make predictions about the behavior of the universe at the Planck scale, which can be tested against observations of the CMB and other cosmological data. One of the most intriguing aspects of cosmic inflation is its potential to provide insights into the nature of dark energy and dark matter. Dark energy, the mysterious force driving the accelerated expansion of the universe, and dark matter, the unseen mass that accounts for a significant portion of the universe's mass-energy content, remain two of the biggest unsolved problems in modern physics. Inflationary models can shed light on these enigmas by exploring the possible connections between the inflaton field and dark energy or dark matter. For example, some theories suggest that the inflaton field could have evolved into dark energy after the end of inflation, or that it could have given rise to dark matter particles. By studying the implications of cosmic inflation, particle physicists and cosmologists hope to unravel the mysteries of these elusive components of the universe. As we wrap up our journey through the cosmic horizon, let's take a moment to recap the mind-bending concepts we've explored. We've seen how the horizon problem presents a puzzle about the uniformity of the cosmic microwave background, a relic from the early universe. The solution? Cosmic inflation, a rapid expansion that smoothed out the universe like a cosmic ironing board. Imagine a balloon being inflated. Points that were once close together are now far apart, yet they share the same temperature because they were once in thermal equilibrium. That's the power of inflation. Now, you might be wondering, how do we know this isn't just a wild theory? Well, cosmic inflation isn't just a neat idea, it's supported by observations. The patterns we see in the cosmic microwave background match the predictions of inflationary models. It's like finding a piece of a puzzle that fits perfectly. It gives us confidence that we're on the right track. But the story doesn't end here. The universe is full of mysteries, and cosmic inflation is just one piece of the puzzle. What caused inflation? What happened before the Big Bang? These are questions that keep astronomers and physicists up at night, and the answers could rewrite our understanding of reality. So what's next? Stay tuned for our upcoming video, where we'll dive into the multiverse theory and explore the mind-blowing idea that our universe might be just one of many. It's a concept that challenges everything we think we know about existence, and it's a journey you won't want to miss. In the meantime, if you've enjoyed this video, hit that like button and subscribe to our channel for more cosmic adventures. And if you have any questions or thoughts, drop them in the comments below. Let's keep the conversation going and explore the universe together. Until next time, keep looking up. Who knows what wonders await?